Let's do a practice problem using the concepts of circular motion in order to solve a problem with satellites and Earth and orbits and that sort of stuff, space things. So let's read through our problem. First, it's got two parts. I've got a satellite orbiting Earth at a distance of 20 kilometers above the surface. The satellite has a mass of 2,000 kilograms. First, what is the centripetal acceleration of the satellite? And second of all, how fast is the satellite moving? There are lots of ways to solve this problem, actually, but I'm going to show you the first part's pretty straightforward. I'll just solve that part. The second one, I'm going to show you a couple of different options. I'm giving you your constant values here so we all match, because there are some like little rounding errors and things like that that can happen, and this way we're at least closer to comparing values. Okay, so remember your formula, or the key point on solving these problems is remembering that when you have an object orbiting another, it has that acceleration pointing inward, and that acceleration is the same thing as the gravitational acceleration that it experiences. So like when you're standing on Earth and you know that you're accelerating down at 9.8 meters per second squared, if you're out here, that centripetal acceleration is the same thing as your g. So the way we write that is also having to do with our forces. We know that our gravitational force is equal to our centripetal force. You have to start here, okay? Start here. So this means that if I plug in my formula for Fg, that's g m1 m2 over r squared is equal to m AC, and AC is your centripetal acceleration, which is the same thing as v squared over r, or how fast your object is moving, that v, as it moves in its circular orbit around our planet. Okay, so let's start here and work on that acceleration piece. First thing I'm going to think about here is what is this m when I say MAC? When I'm doing this, I'm thinking about the satellite. I'm looking at the satellite's perspective. So we're going to call this MS. One of these, let's say M1 is Earth, and M2 is the satellite's mass. If I've got M's on both sides of the equation that are the same value, I can cancel them. So the fact that there is a mass of 2,000 kilograms, it does not matter. This is why algebra is your friend, okay? So let's rewrite this so I can say that G mass of the Earth over the radius squared is equal to AC. Hey, now I've got my centripetal acceleration by itself. I can plug in my values and be done. There's one tricky thing about this, though, is what does this R represent? R is going to be the radius of the Earth plus the radius of your orbit. Okay, we know what the radius of the Earth is, and we know what the radius of the orbit is. It's 20 kilometers. If I'm going to write that in scientific notation, 20 kilometers is the same thing as 20 times 10 to the third meters. I want my units to match, so this is in meters. I want this in meters too. Great, let's plug in. So I've got G, oops, let's just go ahead and plug in values, Nichols. So now I can say that AC is equal to 6.67 times 10 to the negative 11th for G. And then the mass of the Earth is 5.97 times 10 to the 24th kilograms, yikes. And then radius squared, don't forget to square. Remember, I've got to do radius of my orbit, so that's going to be 6.37 times 10 to the 6th plus 20 times 10 to the 3rd. And then I'm going to add those together and then square them. When I do that, I'm going to get a centripetal acceleration value of 9.75 meters per second squared. Hey, remember how it was originally 9.8 if you're just standing on Earth and you're on the surface of the Earth? Now it's just a little bit less. Those satellites are experiencing almost exactly the same acceleration that we're experiencing on the surface. Okay, it takes a lot for that gravitational attraction to go away. Well, it never goes away, it's infinite, but for it to become negligible. All right, so now let's talk about the two different ways that I could solve for this second part, which is the how fast, the velocity piece. I'm going to erase some stuff just to make my life a little bit easier. I don't need this part anymore. I need space to think. Okay. I'm going to leave the bottom stuff there, though, for now. But I don't want my stick figure anymore. Okay. Great. So two different paths you could take. Let's talk about the easy path first, which is that you know your AC value now, and you know that it's v squared over r. So I solve algebraically, and I know that RAC is equal to v squared. So if I do a square root on both sides, I can know my velocity is the square root of r, the orbit, times that acceleration value. Okay, that's the simple way. What if you didn't know your acceleration yet? What if you were solving this backwards? Well, you could start here actually, and you could plug in for AC as v squared over r. So now I've got an r over here and a squared over here, and that cancels. And I've got a square, so I got a square root. So if I say v is equal to g me over r of our orbit. Let's plug in both of these and let's compare the values just so you can see how similar it really is. Okay. Okay. So for the simple one, that's going to be square root of that 6.37 times 10 to the 6th plus 20 times 10 to the 3rd. Add them together and then multiply by your A, which is the 9.75. When I plug that into the calculator, I'm going to get 7,893.19 meters per second. All right, let's do the other one. This one is going to be a square root of 6.67 times 10 to the negative 11th. My mass of the Earth is 5.97 times 10 to the 24th. And then I've got to divide it by the radius of the orbit. So I'm going to remember to add my two radii together. 6.37 times 10 to the 6th plus 20 times 10 to the 3rd. And then when I plug that into the calculator, I get a value of 7,894.04 meters per second. I have a change of less than 1 meters per second. This is just rounding differences, essentially. So I would accept any of these values, right? Like they're practically identical in terms of mathematics. So that way, two different ways, two very similar answers. It doesn't matter. Physics works. Yay. That's pretty much everything I wanted to show y'all. Good luck on those problems.